I hope I can be 3/4 as good as Katerina. So yes, I thought I would talk about one of the, so we know categorification is what we're talking about this week and next. This is the most famous sort of application of categorification. And it's what's nice about this is that it's really a calculation. It's not rich structures, Buddhism philosophy. It's really like just get your hands dirty, do a calculation, and disprove Lusztig's conjecture. It's all there's a lot going on. And one thing is that I'm going to follow like Alistair. I'm going to be like, okay, diagrams tell you a lot about categorification, and I'm going to take it so far that I'm actually going to never use the word category, except to say Hecke category a lot. But for me, category is just a diagrammatic algebra. So I'm going to tell you a bit about diagrammatic algebra and how we use it to disprove Lusztig's conjecture. So what is diagrammatic algebra? So it is taking things that you want to prove and coming up with pretty explanations for them. So I've started with the Fibonacci numbers here and a famous fact about them, which is that if you sum the squares of the first k Fibonacci's, the answer is equal to the product of the kth and the next Fibonacci. So, and this has got a diagrammatic proof. And how does it work? Well, you draw the squares on the left-hand side to make the rectangle on the right-hand side. And then the only bit about the Fibonacci's you're using is that you arrange these squares in such a way that the sizes of these things add up to the next Fibonacci numbers. In, for example, if you look for 5 Fibonacci's, and I've arranged them so that F4 and F5 are next to each other, and so they sum to be F6. Okay, and so that is a diagrammatic proof of a classical formula, and it's sort of just a bit of fun, really. But I thought I'd introduce the Fibonacci's at the beginning because they're going to turn up later in the course. In particular, the golden ratio arises as this limit of the Fibonacci numbers, and you can see this on this picture in terms of this logarithmic spiral. And there's actually a closed formula for the Fibonacci numbers, which is this. And this closed formula is going to turn up in our disproof of Lusztig's conjecture at the very end of the course. And this proof work, this disproof, I suppose, is basically coming from the Hecke category. And what happened was Geordie Williamson showed in 2011, published in 2013, that you can find Fibonacci numbers as appearing in terms of intersection forms of the Hecke category. And these Fibonacci's appear there, and because Fibonacci's have, you know about their prime divisors, you can find p-torsion. And these are all in scare quotes because you don't know what any of these words mean yet. But the whole point of this course is that you will know these scare quote words at the end. So today I will tell you what is the Hecke category. Tomorrow I will calculate some easy intersection forms and show you what they're all about. And Friday I will show you how to get the, and I'll show you some p-torsion tomorrow. And then Friday I'll show you these Fibonacci's appearing in this context to disprove Lusztig's conjecture. Okay, and my entry point for this is going to be lots and lots of combinatorics in terms of paths and tableau. So I'm going to today build up towards the full definition of the Hecke category slowly in terms of paths. Cool. Oh, did anyone have any questions about what we're going to do or when we're going to do it? Or shall we just get on and do it? Okay, cool. So, Hecke categories are constructed from parabolic Coxeter systems. I'm not going to tell you what one of those is. I'm just going to show you my favorite one. Well, it's SA cross SP inside of the symmetric group on A plus B letters. And here is a very concrete example where A is 2 and B is 3. And what I've drawn is, so it's a parabolic Coxeter system. Here is the Coxeter group, S5, and it has a parabolic S2 cross S3, where S2 is the transposition 1, 2. S3 is generated by the transpositions 3, 4, and 4, 5. And so, of course, this parabolic fixes that little picture at the bottom where you act by permutation. So if I swap the first two symbols there, it's fixed. If I swap the third and fourth, or the fourth and fifth, that is also fixed. But if I swap using the pink one, the one that is not in the parabolic, I get something new. So if I swap the second and third, I get something new. And so I can diagrammatically construct the cosets graph of this guy using reflections coming from, well, stop the system. And I use the colors to record what reflection I've used. So here, if I use 2, 3 to swap the second and third things, I draw a pink line. If I use 3, 4 to swap the third and fourth things, I use a green line, etc., etc. And so this is the Coxeter graph for this parabolic Coxeter system. And this is the Brouillard order, which is basically use these reflections coming from the Coxeter system and record how many of the reflections you use to give you the height in the graph. Cool. Now, Lustig theory is the study of paths in this graph. So here I've shown you a path which goes from the bottom, it goes all the way up, leading to the right, to the top. And the color sequence it did was pink, green, orange, blue, pink, green, ta-da. And so I write that this path is given by pink, green, orange, blue, pink, green. And I use U to say that I've gone up. And I use 1 to say that I really went up. You'll see what the 1 means when I don't use the 1 next time. And I write that the weight of this path is just the path itself, again, vacuous in this case, and the shape is the point at which it terminates. Cool. Now, I've used the term shape and weight here because Sandy Green in 1990-ish wrote down a basis, the codeterminant basis of the Schur algebra, and essentially the way I'm going to construct this Hecke category goes back to Sandy Green. It's all in terms of weight, giving you, so no need to check put the lights on, but I'll just draw a little picture. So cellularity looks like this. It's a construction where you draw things like this. And weight is always the outside bit, and shape is always the inside bit. And we're going to see this picture later on. Okay, so let's see some more paths. So I'm now going to take the same color sequence, pink, green, orange, blue, pink, green, to terminate at a different point now. And okay, I write again. So I went up pink, and I really did go up. I went up green, I really went up. Orange, I failed to go up. So I say up 0. Wanted to go up, but didn't. Then I did go up blue. I didn't go up pink. And then I did go down, right? So that's what that ups and downs mean. So I was going to do something, it tells you if it's up or down, and the 0, 1 tells you whether I did it or not. And here I write that the weight of this path is actually just the path on the previous slide, because the color sequence I used was identical. So this is the color sequence, but the shape is where it terminates. Okay.
Is there a distinction between up 0 and down 0?
Oh, so you mean in here? So up 0 is when I didn't go up. Mm-hmm.
Is there a down 0?
Oh, down 0. Let's see. Oh, and notice that I put +1s whenever there was an up 0, because that's going to contribute to the degree by adding to it by 1.
So what do you mean when you said weight is T of x? What is T of x?
T of x is the path from the last slide that went pink, green, orange, blue, pink, green, all the way up. So T of x was the previous path.
So this one's the same way?
Yes, so this is the same way, because it's obtained by folding up the original path. So is we're going to answer both those questions, I guess, again. So pink, green, orange, blue, pink, green. So if I'd done those things just all the way up, I would have got the path Tx from the very first slide. So I say that the weight of this new path is Tx, because if I had done all of them, pink, green, orange, pink, green, I just select path Tx. And in this case, the shape is where it terminates, which is now Z. And notice that now I actually, when I did down 0, which was don't go down, this now has a -1. So I say that all the steps in this path have got degree 0, +1 or -1, depending on whether they, if I do them, whether they go up, whether they go down, whether they don't go down, in a way that I'll write on the next slide. Okay, so let's just do it for this particular parabolic scissor system to get going. So for lambda, a point in the graph, we're going to say that it has an addable node that is pink if there is an upward edge coming out of that node lambda, that point lambda, and it's pink. We say it's a removable node if the edge going out of lambda goes downwards. And then there are 4 ways to walk around in the graph. Namely, do go up, fail to go up, do go down, and fail to go down. So I'll draw them here, but U1 is that, U0 is that, D1 is to go down, remember, and D0 is fail to go down. And they have degrees +1, -1, and 0 otherwise. And we're going to let the shape of the path be the point at which it terminates, when I folded it up, and the weight be the color sequence of steps done in turn to create the path. All of the paths we've seen so far were of shape Tx. They went like so. That was the weight. So let's draw a picture. So I think I'll do one more slide and then I'll pause for thought. So we're going to talk about how to construct it. Okay, actually, let's pause for thought there. Does anyone have any questions? Yes? Sigma of any reflection in the so if we go back here. So at this point, sigma here is genuinely pink, okay? Now sigma is green, sigma is orange, sigma is blue, sigma is pink, sigma is green. So somehow just the color at each point that you're interested in. Cool. So that's the algorithm for writing down a path. I'm now going to tell you, oh, sorry, yes?
What do you do with colors that are not an adder?
You don't do them. So I'm never going to do colors that are not an adder. Okay, so now I'm going to tell you how these little paths give you Zergel diagrams. Okay, so let's go. So let's start with the case when I could add, so the U0 and U1s. And so far, my path has got to a given point of a given shape. So I'm going to define a new path, a new diagram, a diagram from this path. So take your old diagram that you deductively constructed. If I do add U1, I just draw a pink strand next to it. And notice that, that's fine, I'll just leave it there. And if I don't go up the strand, if I don't go up, if I fail to go up, I take the old diagram, I draw the pink on the bottom, but because I failed to do that step, I'm not going to do the pink at the top. And so because I just want to not just let it float into nothingness, I draw a little spot here as to record that I was going to do the pink, but then I failed to do so. Okay. Now, what if it's the other one? What if I could have gone down? So what about D0 and D1? Well, if I fail to go down, well, what happens? So the diagram S, the existing diagram, already had a pink at the top, because what I did so far, I must have done this at an earlier step. So now what I'm going to do is I'm going to say, add this new strand. If I fail to go down, it's because I joined that existing pink, but stay there. So the color sequence at the bottom and the top here, the color sequence at the top matches the color sequence at the top after this. If I do go down, I have genuinely removed a color. So I do that with spot bulk. This shouldn't be very clear at this point, but I think the next step, the example, will help. And I'm just going to say that the shape of the path will be recorded across the top of the graph using that color sequence, and the weight will be recorded at the bottom of the path. The path weight will be at the bottom. This shouldn't be clear at all. This is horrible. Let's just do the example and it'll be completely clear. So we're going to do the path from the previous slide. So we're going to go up means add a new strand. Doing up means add a new strand, so I add it. Not doing up means adding a new color, but then aborting because I'm sort of like, oh, I was going to do it, but I didn't. Now, here, I'm adding a new color, blue, great. Then I fail to add the pink. Now here, what I'm going to do is I'm going to genuinely remove this green here and get, so notice that at each point, so this now terminates at the point pink, blue, and so that's the shape, and that's the weight. Like so. I noticed that this was the path that I drew on the previous slide where I went up pink, up green, failed to do orange, do blue, failed to do pink, do green. And so it terminated at pink, green, but the weight was pink, green, orange, blue, pink, green. Okay. Now the other one that I'm going to do is so that was the path that terminated at Z on the previous slide. And okay, the path that terminated at Y was exactly the same to be starting with, but then I did go down, then I did bounce at the end. So that would be the path that went pink, green, don't do orange, do blue, bounce on the pink, don't do that, and then bounce on the green and go back to that. So now this guy at the top is pink, green, blue. This is longer. It's actually just, so notice the height, the number of colors at the top tells you the height. That's height 0, height 1, height 2, height 3. So that guy has 3 colors at the top. Here, this is height 0, height 1, height 2. So that does have 2 colors at the top. Okay. And I'm just going to go back to look at those 2 paths, just to remind us how this connected to that picture over there. So here we go. So this was pink, green, don't do orange, do blue, don't do pink, don't do green. So this one here corresponds to this picture here. And this is the one where we did straight line, spot, straight line, spot, fork, spot. Okay. So, are there any questions about the combinatorics we've done to construct these diagrams? Sorry, could you speak up?
I'm worried that there will be some relation.
I have purposely chosen a parabolic Oxford system which is fully commutative, so there are no breaks. Never gonna happen. Apart from commuting. So I have no grades so far, and here's the picture. Any other questions?
And we could interpret these paths. I'm sorry if I missed you saying this as like up down tableau, partition sitting inside the rectangle.
Yes, you can. I'm not going to draw it because I didn't want to add the other way of thinking. I didn't want to add that way of thinking. But yes, you can think of. So we might as well draw it since you brought it up. So if I draw my permutation, so remember this was S2 times S3 in S5, everyone. So what's the longest possible coset for S2 times S3 and S5? Well, you draw some straight lines, you cross everything, like so. And so you can actually think of this as a rectangle, as Ben was just saying. This isn't going to be needed in the talk, so maybe it was a bit of an unnecessary digression, but notice that if I...
We were talking about shape, and you really mean shape of the partition.
Yes, that's why I'm using that notation. So when I say sigma is addable or removable, it's a genuine addable or removable box for a partition in this picture here. So here, this is, you can think of this as the, giving you the shape, which is that. So notice there's a crossing in this box, if you like, a crossing in this box, etc., etc. So here, lambda is genuinely a partition that fits into a times b, or 2 times 3 in this case, thing, but that's not going to be needed, but it's sort of where the idea comes from. So you don't need anything to do with the partitions that I just spoke about, but who is happy with how I came up with this from a path? Can we put our hands up? Yeah? Okay, cool. Okay, that's the only thing you need to know so far, so that's okay. Okay, so the Hecke category is, for this particular case, remember I avoided braids. So fixed WP like so. The Hecke category is the span. Well, okay, it has basis. So remember, when I say Hecke category, I'm talking about a diagrammatic algebra. So categories are just algebras for the most part. I'm going to take the diagram I showed you how to construct, corresponding to a given path that terminates at lambda, and I'm going to take his friend, which is just obtained by flipping him upside down. So star means flip it upside down, put that on the other side, so that I have something of the form CS star CT, like so. So I'm going to take diagrams which are formed from parts of a given shape and other parts of a given shape, which terminate at points in this graph. And this is going to be a basis of an algebra which we call the Hecke category. Okay. So this is the Hecke category. There you go. You now know. It is draw some paths, draw some diagrams associated to them, sometimes flip them upside down, concatenate, and you now have a basis of something called the Hecke category. So are we happy with this just being the diagrams we all just said we were happy with, flip, and their friends flip on their heads? And this is very much of the spirit of Green's original definition of the codeterminant basis, which looked like this. So it would be, he defined it like so. It's the same thing, it's just a cellular algebra. Okay, I haven't told you what that is yet, but it's just diagrams and their flips. Cool. And it is a cellular algebra, which just means that if I consider all the points below a given point in the Brouwer graph, so fix mu, any point in the Brouwer graph, consider all of these things of shape less than or equal to mu. This is a two-sided ideal in this algebra. And that's the definition of a cellular algebra, basically. There's no missing axiom there, I don't think. I think it's complete. So this is a cellular algebra in the sense of Graham and Lehrer. Or if you prefer, because you're categorical, this is a object-adapted cellular category, where object-adapted just means that there are lots of idempotents floating around here coming from these points.
told us what the multiplication is in this argument?
No, I have not. That is the next slide. So this is the basis, and I'm going to tell you how to multiply shortly.
You would say it's a two-sided ideal, right? So it doesn't mean anything.
That is true. But so let's talk about cellularity first, and then multiplication later. But quite right. Okay, so diagrams make nice bases. And notice that, in particular, all of these diagrams are formed from straight lines, spots, forky things, because that was my, well, up 0, up 1, down 0, and of course sometimes I had to cross strands, and so these are the, in fact, generators of this category, in the sense that I drew some pictures, and this is what the pictures look like in local regions. And now I'm going to tell you how to multiply, probably. Cool. So now I'm going to tell you how to multiply. Oh, no, I'm not. I'm going to show you the basis in a particular case. So why don't we do the stupidest possible case? We're going to do the symmetric group of 2 letters. Here's just the identity of S2 and the element 1, 2. And if you do not know that, it's there. If you don't know that, you're probably not going to get anything from this talk anyway. So the idempotent, which is going to be the identity of this algebra, is labeled by the points in the graph. So you've already seen the idea that blank space, drawing nothing, is the monoidal unit. And the empty path, which terminated at the identity, is just blank space. And there is the monoidal unit, which is an idempotent labeled by this guy, which is blank space. The only other vertex in the graph is transition 1, 2. So for pink 1, 2, top and bottom, the idempotent is just the strand. And that is going to be the identity of this algebra. And I've sort of just included this little thing here, which you can ignore. Just be like, this is the identity of the algebra. This is sort of a proviso so that experts don't tell me off. But this is the algebra, and there are only 3 paths, right? The empty path where I did nothing, the path where I go up, we've seen both of those idempotents. Then there's the path where I fail to go up. And I'm going to construct all the elements of the algebra using those 3 paths. So we've already seen the case where I go up, done. We've already seen the case where I don't do anything. But I can also fail to go up. I can turn that upside down because we had this anti-involution that turned diagrams upside down. And I can times those 2 together. If I put that one on top of that one, I get that one. And I claim, well, that this is the basis of this algebra. And I claim that this is a 2-sided ideal with some multiplication that I haven't told you what it is yet.
So the notation of HS2 here means
Hecke category labeled by W being the Weyl group being S2 and the parabolic being trivial.
so what's the dimension?
So yeah, if you actually did this without truncating, that you'd be able to define some monoidal category which is infinite.
Yeah.
But in this talk, I only ever want to consider finite things, and that's the little trick I did to do that. So now I'm going to tell you how to multiply in this algebra. There are some relations. And what do these relations do? The whole point of these relations is to give you this basis. We want to somehow categorify paths in this graph. Why? Because paths in this graph are what define the Castellistic polynomials. And we want to somehow understand Castellistic theory in a categorical setting. So everything you need to know about this category is just somehow trying to rewrite the thing so that the basis is the basis I told you that it was, which is why I'm telling you the relations after the basis. The basis comes first, and then these are just the relations that you do to give that basis and honor the grading. So I told you that these things have degree plus or minus 1, well, that puts a grading on the algorithm. That makes sense. So here, This fork, remember, he had degree -1 because he corresponded to failing to go down. This spot had degree +1 because he was failing to go up. And so when you multiply them together, you want it to be something of degree 0 with the right top and bottom. Well, that's an obvious element, isn't that? Now here, what I've done is I've taken two things of degree -1. I don't want to go all crazy and start like having billions of diagrams. I want 5 at the end. So I want to think of one of the two possible ways of starting at double pink and ending at double pink and just say, oh, they're the same if they have the same degree, which they do. This with -1, -1, -1, -1. So all you're doing is picking the only way of drawing a diagram so that the top and bottom match. And okay, here, this one is something different. It's starting at the same place, ending the same place, but with scalar 0. So it disappears. And that's because the only map you want from starting at pink and ending at pink should be the identity. And this has got degree -2, and oh god, what am I going to do? So I'll just kill it, and then I'll be fine. Okay. Darkness fell. Let's see if there we go. Cool. And okay, there's something else, which is, oh god, I've never seen one of these before. But clearly, if I put diagrams on top of each other, I could create one of these guys, because the spot exists, so I could flip it and see what happened. And I just want to be able to make sure that if a spot ever did, a barbell did ever appear, a barbell like this spot, notice that if you go to the gym, this is a barbell. This is how I remove any possible barbells from my diagram. So I guess the message is don't go to the gym. Once, I also take the relation that, so here I had a barbell to the right, I moved it to the left, and then I say once the barbell gets all the way to the left, it dies. So any diagram has, if it has a barbell in, you move it to the left. Once it gets all the way to the left, it dies. And anything it produces on its way to going to the left is barbell free. So our spaces have no barbells. And that's the multiplication rule for this Hecke category S2. Let's show you a nice little example. So here is, oh no, this diagram is huge. It doesn't look like any of the 5 that I showed you. But notice that whenever I have a barbell and a spot, that's the thing where I was like, well, that's just the identity. So I can suck it all back in, and then it's just this strand here. Oh, but he's got a barbell in there, but I told you that I could get rid of any barbell. Notice that I move that to the left, it breaks the thing up. And once it's all the way to the, you also have the diagram where it is on the left, but that's 0. So there you go, that's some multiplication in this Hecke category. So who has questions on the one color Hecke category, this 5-dimensional algebra with these rules to tell you how to multiply in a nice graded way?
You mind how you use degree? It's a degree -2. How did you?
So the degree comes from here. Any vertical strand by itself has degree 0. Any spot has degree +1. If I go down, but bounce, I create a fork, and that's degree -1. And in fact, 1 plus -1 creates this spotted fork of degree 0. And so you just look at your diagram, you sum up all the number of forks, and that's minus something. Then you sum up all the number of dots, and that's plus something, and then the degree is the difference between those two. And notice that the parity, well, I think not parity, the sum of spots minus forks is preserved here, meaning the degree is preserved. This is homogeneous. Yes?
So this is just a regular one color Hecke category.
Yes.
Why is barbell always the left 0?
Oh, I am looking at the finite dimensional case. This is Zergled modules, if you like, not Zergled binaries. Okay, so one color done, but we want more colors. So I'm going to need more relations when I do this. So remember, it's still spanned by just those diagrams I've shown you how to do with 2 colors. But now I need more relations in order to write any possible picture simply in terms of the ones that I told you in the basis. So we're going to need an analog of this moving barbells leftward rule. There you go. That's it. I've got no intuition to offer here. You needed something. There it is. Just then, okay, I now need something to tell you that, okay, if I do pink, blue, pink, that is not actually going to be a step in my graph, because if I do the pink, and then I do the blue, and I go upwards, oh, I'm not going to be able to add another pink. And I'm not going to really explain that, but if you think about this picture that Ben highlighted, it's obvious, because what you end up with is a partition which has pink, blue, pink in it. And I call this the Temperley-Leave relation because, oh, okay, if you drew this in terms of Temperley-Leave diagrams, you'd see that it contracts away to just be pink. It's just there for a placeholder. We're not going to really think about it too much, but you need a relation for getting rid of these sort of things. And everything else is just the commuting relations. If these colors, blue, green, and orange, commute, then you just say everything within the diagram commutes. So there's only two real relations here of any interest. One is the two-color version of something we've already seen. Colors that commute, commute. This is something funky, which will be replaced in a moment anyway. And then, okay, we need one more rule, which is now that we have a parabolic, namely SA cross SB inside of SA plus B, we say that if you start with something that isn't the first color, it isn't the color outside of it. Any color in the parabolic, if it's all the way to the left, it's 0. Why is that? Because I want all my paths to start by leaving the parabolic, right? Everything started with pink in the graph you've seen. That was because it was the only color not in the parabolic. And if I want to only have paths coming from the parabolic Coxeter system, I have to kill everything where, if I were to do it, I would make no progress. I'd stay in the parabolic. Okay. So let's construct a nice representation of this module now, of this algebra. So are there any questions? I know it's sort of vague, but you wouldn't believe what I'd have to teach you if I was going to actually do it properly. So the idea is, oh, there's some pretty relations in a diagrammatic algebra, and they give you this basis.
Go back to the multiplication for a second.
Okay. This particular example.
Yeah, so we were talking about this, maybe you said it, but so you're really multiplying two elements by stacking, right?
Yes.
And then you would end up getting some complicated diagram like this, and then you would apply all the relations.
Exactly. So stacking is the multiplication of the algebra, modulo these relations. And there they are. So now I'm going to show you how to construct some of these representations for this two-sided guy. So here, what I'm looking at is the parabolic Coxeter system for S2 cross S2 and S4. So there's only one not in S2 cross S2. I'm going to show you how to construct a representation of this category algebra. So I'm going to show you how to construct the one corresponding to this one here. So it's going to be generated by just this guy, this idempotent path. So that's all the paths that you can do, which are of shape pink and end of pink, right? If I draw a line, the only way to fold it up to say where it is to do nothing. It's a bit vacuous, so it's hard to understand, but hopefully it'll become obvious for next one. So the other thing I could do is I could draw a path that went pink blue and fold that up to now terminate a pink. So now I took the path pink blue, folded it up, notice that it got pink blue across the bottom, and this is the way I told you to construct something corresponding to this. Okay. The other thing I could do, which is kind of obvious, is I could go pink green and fold him up, like so. I could also do pink green blue, fold him up twice now, so do the pink, fold the blue, fold the green. Okay, and finally, I could go all the way to the top, and I could fold him up by do the pink, bounce the blue, bounce the green, bounce the pink, and with this diagram here, and notice that, well, okay, don't notice, but okay, here's a fact. what we've actually constructed here is a cell module for this algebra. We've constructed one of these layers, I told you, part of this basis by saying, okay, let's take all the possible paths in this graph that can be folded up to terminate at that one point. And notice that how do I get from this guy to all of these? I can obtain all of these diagrams by concatenating on the bottom to get a diagram. So if I put this diagram below that one, I get this one. If I put this one below that one, I get this one. And so what I'm doing is just this concatenation on top of each other gives me a way of moving down the algebra, and it can't be reversed. And so, for instance, here, if I put a pink spot here, that will contract that all the way using the relation I showed you to get that diagram. And so this is a representation of this algebra.
So Chris, how does the 2, 3 tell me where you're going to end up?
So the 2, 3 is the top of the diagram, and notice that all these diagrams have just 2, 3, the pink at the top. And what I've done is I've shown you all possible ways of folding up a path to terminate at 2, 3. So there was the one where I did nothing, the one where I folded here, I folded there, double folded, and then this long triple fold here. Okay. Still not told you the actual Hecke category we're interested in yet. So one last thing. So as we got pointed out very near the beginning, if I'm not taking this maximum parabolic, then there are 2 ways of writing down the element, the longest word in S3. I can go pink, blue, pink, or I can go blue, pink, blue. And I want them to be the same in some sense. So I add this new generator of the algebra. And what are the relations? Well, notice that this is actually Temperley-Lie relation. And the point was that in the Temperley-Lie case, there was no way of writing down pink, blue, pink. But in this case, there is. You can braid twice and end up where you started. So if I swap S1, S2, S1 to the S2, S1, S2, so and then I swap back again, well, I can rewrite this in order to get the basis that I want. I can rewrite this in this way. So this is a new relation that comes about when I add this new generator. This replaces the one where this was just 0 before, because that element was 0 in that Hecke category. And I need some extra relations, which are just something to do with making sure degrees match up, but I don't want to talk about them. And then there's this big one, which is horrific to look at, but it's actually beautiful. What it's telling you is that because I'm taking the longest word in S3 as a generator, so for the symmetric group itself, we use Coxeter generators to generate. They've got length 2, and all the relations have length 3, right, for the symmetric representation. Here, I've now got a generator of length 3, so I need a relation of length 4. Now, S4 acts faithfully on the permutahedron, which is the truncated octahedron. And so the 2 different ways of writing down the longest element in S4 can be drawn on the permutahedron. And when you look at these pictures, they give you this relation in the Hecke category. So this is the analog of saying that permuting that way is the same as permuting the other way. So that is the braid relation in S3. But now I need the version of in S4, which is the 2 longest ways of writing down the element of S4, are the same. And you can picture this as making these permuting. So let's show you an example in my favorite group, which is affine symmetric group on 3 letters, quoted out by the parabolic, the finite S3. So I said that everything was given in terms of paths. So let's draw the first guy corresponding to going all the way up. So if we go all the way up, I only add vertical lines next to each other, remember? And oh, for funsies, I'm going to add a final green line. Now, if I want to move around this graph, I want to think of folding up paths the way I did for the maximal finite parabolic case. But now I've got this path blue, green, blue, which I want to be the same thing-ish as green, blue, green. So if I want to fold this path around this little hexagon here, I use this generator, which looks like the one that we've just added in order to get the full symmetric group thing. Okay, well, now what if I want to fold things up in the old-fashioned way? If I just want to put a blue spot, well, then I can do that. And okay, I can also use forks to get rid of these extra lines. And I can also use this new generator to get these things where I swap around the hexagon. So what should you know about the full Hecke category? All you need to know is that it's got an extra generator corresponding to moving around in an extra way in this path for these parts. And okay, there's some other relations that I haven't really told you much about yet, other than the commutator, because it's pretty cool. So now we're going to revisit the point from earlier in the talk, which is that we've now got braids to worry about. So most of it's the same, no change there. But if I've got a removable color from a point in the graph, I now have to be able to construct a diagram from that. And how do I do it? Well, this is the old picture that I showed you, except I just need to remember now that not all diagrams have a pink that I can remove. So I just have to add the, okay, commute to get the removable pink from your diagram and then remove it. So it's exactly the same picture as I gave you earlier, except with a braid. And the braid is just this one here. So here, I wanted to remove this green eventually, but in order to do it, I had to swap this blue, green, blue to get, there's a braid, and then, okay, now I can remove it. So I'll show you another example of that. So here is our same thing. I'm going to tell you how to construct a path. So pink, you just add the pink. Blue, you just add the blue. Green, you just add the green. Blue, fine. Now I want to bounce this pink, and notice that because it's I can just do that. That's not hard. If I want to remove this blue now, I can also do that. That's not hard, because there's a blue there to join it to. Now what I'm going to say, all that I've been telling you from this past slide is just so that I can now take care of, what if I wanted to go down here? Well, green isn't removable here. So I try to remove it and can't, and then I just stick in the extra generator. So it is removable from this picture, not from that one. So I just swap the picture out. And that's the only difference in the full Hecke category to the one with the finite maximal parabolic case. You sometimes have to stick in braids in order to do what you want in the graphs. So, I don't really know how much time I have left, but this is just to say what we've learned. So, the object that we're going to be interested in, the Hecke category, is generated by these diagrams. I've shown you that, okay, these are what these paths look like. They give you these diagrams. Subject to the relations, which were the ones that we've just listed. And, okay, the cellular basis goes through in exactly the same way. There is a cellular basis. It's indexed by points in the Bruchar graph under the Bruchar ordering. Okay, and because this is a cellular algebra, the Graham-Layer machine, which you crank out, tells you that it's got simple and standard modules labeled by the points in the Bruchar graph. And we've seen an example of one of those earlier. Okay. And what we're going to be interested in is the composition factor multiplicities of these standards, the simple composition factor multiplicities in these standards. These will be the p-Kazhdan Lusztig polynomials of Lustig's conjecture. Okay, and this is all I wanted to say in the first lecture, and I know that I've said it very fast, but the only thing you need to take away is there are pretty pictures, you use paths in the graph to construct representations, and okay, these aren't simple, but they have simple composition factors, as you would expect. And the point of Zergel's Lusztig's conjecture mostly, is to understand those composition factors in those representations constructed from paths. And I'll just show you how to think of the braid relation that I showed you earlier. So here is pink, blue, pink. Now, when I pass from here to here, I've shown you that what I do is I think of that as something to do with this three-color diagram here. And if I pass back to where I started, you might think, oh, well, that might be the identity. Why not? Why is it not the identity? Why is it not that if I put a braid on top of the braid, it's just identity? Where is this error term coming from? Well, it's coming from the other way of folding this diagram. Start with pink, blue, pink. You can fold it by going pink, add to the degree, remove to the degree. So this is the degree 0 diagram, which takes you from here to here. And I can also undo that guy to get back to where I started. So putting that on top of that is this temporally lead fella that we were talking about. And notice that this is a degree 0 morphism of paths from this guy to himself. There's, of course, the identity is another degree 0 morphism of paths from this guy to himself. But they're not the only ones. The case is not that you might think, oh, okay, well, I've got this braid, it's something to do with paths. If it were invertible, wouldn't that be great? If I could just say, doing that is boring, huzzah, that would be easy. But I told you the way to think of these relations is to think of trying to get exactly the basis you want using some sort of local relations. The thing that is missing from this is that there is another possible path, and I said it had to match the degree. We wanted something homogeneous. This is another way of folding a path from there to itself of the same degree. And in fact, you want to be able to put all of these guys into a relation, right? You want to say, okay, if I'm going to start pink, blue, pink and end pink, blue, pink, there are 3 ways of doing it. And in fact, any relation that gave me this path basis would have to involve all 3 of those diagrams, and lo and behold, it did. And that's why this was the relation that we added once we added the braid generator. It was just the only thing you can add in order to get the path basis you want. Okay, so that was a little justification of that. Now, these are the things that I would like you to know at the end of this lecture. There's, what are they? You need these diagrams in order to think of paths as giving you some algebra. This is what every region in this thing looks like, subject to those rules, up 0, up 1, down 0, down 1. There are some relations which are only there to get you from all possible diagrams looking like this to the ones which look like the paths. There's a basis, which is exactly the basis that we wanted to get using these diagrams. The layers in this chain of 2-sided ideals give you something called cell modules coming from the grain and layer machine. And because each layer had an idempotent, where I just did straight lines, every one of these cell modules has a simple head, again coming from the grain and layer machine. So we've got representations of a pretty picture algebra. The subject of Lusztig's conjecture was, what are these pretty representations in here? What are their composition factor multiplicities? Lusztig conjectured that they would be characteristic free. We haven't spoken about this at all, but just to bring back to where I started, conjectured that these multiplicities were characteristic free some of the time. And he was wrong, and we're going to show you that on Friday. But for today, nice diagrams, nice basis from paths. Basis gives you nice representations using grain and layer. The thing that I told you that this whole lecture course was on was how to pass between one family of representations to another. And in what sense this will depend on the characteristic of the field for the algebra I'm looking at. Okay, so hopefully we got something from that, which is nice diagrams, nice representations. We'll actually play with these representations tomorrow. That's what intersection forms are. They're multiplying these representations. And then maybe you'll understand some of what this lecture was about. And by the way, the slides for this are available on my website, and there's a link on the thing. So you can look at these pictures and go through it more slowly and maybe stack some on top of each other and play with them yourself. And then maybe some of what I said will become more